All right. So my approach here in advanced control systems is to actually work with the problem, advanced problem, so that all the bits and pieces we study in control system design and development uh, can be properly placed. Okay, so then you know how these different parts are fitting together. For example, modeling, controller design, simulation, different types of controls, sensing, and optimization. A lot of things in on the table. So you pick up different components and fit together when you deal with a control system. So that is why this part is extremely important. A lot of things going to be fitted together here. So we saw this problem last week, right? I'm just going through, skim through it, not going into details because we have already covered it. The problem we are having is this cart pole problem. And sometimes you call it inverted pendulum, slightly different version. Here there's a cart so that you can pull it, push it left to right. And the purpose is to uh, balance the pole on it, okay, vertically. So that is number one objective, stabilization. Number two is that you have to move the cart to a desired position and you have to stabilize the pole there, okay. So therefore, this is a bit tricky. Now, what we did was we tried modeling the plant. We wrote equations, right, for the pole, right, that is actually pendulum, inverted pendulum, and also the cart. Cart is moving on the horizontal plane line, actually one-dimensional, and the pole is actually rotating. So then you figure out different coordinate frames also, right? One is, you can say XY, the other one is actually angle, right? Again, you wrote the radially outward vector and tangential vector, and then transfer the coordinates to X and Y. So all these things that you learn in your say early courses, right, you cannot drop anything because you're going to need it now. Okay, so after we deriving these basic equations, we figured out, okay, this is a second order system, but you can see a cart is one system, pole is another system. They are coupled through the pole. Okay, so therefore we have two different systems of equations, right? The first one is actually the acceleration of the cart along the horizontal line. The second one is the acceleration of the pendulum pole, right? Angular acceleration. So when you say acceleration, then actually you deal with the velocity and position also, right? So then we understand this is a second order system because you need position and velocity as your state variables, and rate of change of state variables is actually acceleration and velocity. So if you say position, its rate of change is velocity, and if you take velocity, its rate of change is acceleration. So that's how you figure out your state variables, okay, and their rates of change. So on the right hand side of the equation, you have position and angle, and on and their velocities, and on the left hand side of the equation you have angular velocity, linear velocity, angular acceleration, linear acceleration. Okay, so I think you remember these equations. Uh, say for example, equation number 10 over here, x double dot. This is the acceleration of the cart at any position, right? You have the entire system over here on the right hand side, right? You can see U. This is the force on the cart, control signal actually to the cart, because by driving the motors on the cart, right, you move it this way or that way, and you're giving a certain force there, right? And the mass of the pendulum, angle of the pendulum, right, length of the pole, right, and the mass of the cart, everything is there. The entire system is there, and based on their values at any moment of time, you get x double dot acceleration. And at the same time, if you look at the pole inverted pendulum, it has angular acceleration. Again, you can see on the right hand side the state information, the situation, right? In terms of angle, pole angle, the force on the cart, length, mass of the pole, pendulum, x dot, velocity of the cart, all these things are there. Okay, so to find out how these quantities are assembled together, related together, to calculate acceleration is also something very, very important. Okay, if you can get through these equations and eventually arrive at equation 10 and 11, right, you can be happy about it. That's a really good skill, right? Modeling plants. Then we figured out these two equations are highly nonlinear. You can see sines and cosines, which are nonlinear functions, and you can see theta dot square, right? So it's seriously nonlinear model. Now, if you look at, have we done any nonlinear controls? No, we haven't. Okay. But one thing we did was gain scheduling controls, right? Where nonlinear plant is actually linearized at different states, right? And then develop a controller. So that's one approach, how to deal with nonlinear plants, right? So if you follow through that process, you can linearize the plant. Now, when you want to linearize a plant, you have to make a decision. Okay, what is the desired state? What is the desired state? And desired state, of course, you know, vertically stabilized position, right? X can be anywhere, right? But it should be vertically stabilized. So we say, let's linearize the plant around theta equals 0. So theta is measured from vertical line. So when theta is 0, when the plant is stabilized, angular velocity is also 0, right? And when you set these values in your nonlinear, the two nonlinear equations, theta double dot and x double dot, you get rid of nonlinearity. Okay, eventually theta double dot becomes like this, and x double dot becomes like that. So its system is linear now. And you have to, you should not misunderstand that we are not making the system linear so that we can control it anywhere. No, that's wrong, right? We can control the system around the state where you linearize the model. Okay, remember that when theta goes, say, 30, 40 degrees, right? That is not what you assumed here, right? You assume theta to be 0 or around. So therefore, when you do the simulation controls, if you see, okay, sometimes the pole swings back and forth more than 30, 40 degrees, then you can immediately see that, right, whatever happening, right, whatever you are seeing on screen as simulation is not valid, because the controller is not actually able to cope up with that sort of state change. Okay, right. I think now you are in a certain state of mind so that you can proceed with it. So um, once you linearize the two equations, right? One is for x double dot and the other one is theta double dot. And of course, you know, x dot is a state variable. So is theta dot. You can see it over here. X dot theta dot are the state variables, right? And on here, you have the rate of change of state variables. X rate of change is x dot rate of change is x double dot, like that. So when you do that, in fact, the two major equations here are the second row and the fourth row. These are the two nonlinear equations that will linearized. Okay. And the other two equations, if you see, is 0, 1, 0, 0, and this one 0, 0, 0, 1. This is just to say that theta dot right, is equal to the last state. Of course, it is theta dot. And if you look at the first row here, right, this is to say that x dot is equal to the second state variable, which is of course x dot, right? And also in these two equations, second and fourth, we saw the control signal as part, right? 1 over capital M in equation number 2, right, row number 2, and 1 over capital M times L times U as part of the fourth row here, right? You assemble the state vector, rate of change of the state vector, and the system matrix, and also drive matrix or drive vector. And this is your nice and neat state space model. Again, this is linearized state space model. So you figure out x dot equals ax plus bu, y equals cx plus du, where a is this, right? And if you look at C and D, of course, D, right, we set to 0. There's no direct relationship between U and Y, okay? U is related to X dot in some way, but U is not directly related to Y. By the way, what is Y? Y is the measurement. So you have the inverted pendulum and the cart is moving, and you know there are 4 variables, x, x dot, theta, theta dot. And out of these state variables, what are you measuring? Okay, using sensors. That is why. Now, you can judge what you want to measure. For example, if you set your measurement matrix or vector, right, in this particular case is a matrix C, like this, is 1, 0, 0, 0 in the first row, and 0, 0, 1, 0 in the second row. What you are saying is that you are picking the first state variable and the third state variables to measure. So what is the first state variable? X. You measure X. Position of the cart, you measure. Maybe using an encoder or something, right? And also you measure the third state variable, which is theta. That is the angle, right? The two most important sensor measurements, the position of the cart and the angle. Because these are the variables you want to control. So you got to measure them, right? Right. So if you want to measure another variable, there's another row coming over here, right? So this is the measurement matrix. So your entire model is here, and this is the linear model, remember, linearized model, and this is valid. You can use this to design a controller, but you have to make sure that you are actually starting the pendulum nearly vertical and you are controlling it without letting the pole to swing more than, say, plus or minus 10 degrees, okay? Right. So I think I showed you this simulation. So let me show it again to you. That is this one. Just to recap your memory. This is open loop simulation of the plant using the nonlinear equations. Remember x double dot and theta double dot, starting with some initial precision. Okay, so we just let it go. We just let the pendulum go. So it moves this way, that way, like that. By the way, this is a controlled simulation. So this is not what we want. The code is CartPen Sim. So let's open CartPen Sim I think it's somewhere here. Card pen sim. Where is that? No, this is not what we want. Got it. I got it. So I have made a selection here. So fine. Now let's give it a try. No need to clear the workspace because I have all of my codes clear, close all CLC. So I flush the workspace before I start a new code, right? All right, now you see it. This is without any controls. You just let the pendulum to fall at a certain point, right? So the linearization, those models, not relevant here. This is nonlinear dynamics of the plant, right? Without any controls. There's no control signal here. So please watch it and check if it makes sense to you. Is this what you expect if you just let a pole to drop on a cart so that as the pole drops, cart moves in one direction, and when the pole swings on the other direction, cart starts moving the opposite direction, right? This is pretty much something you have experienced sometimes, or something you can uh, convince yourself, right? And also here you can see the graphs going x and x dot. Blue is x, right? This is a cart moving forward and backward, and the velocity of the cart is a bit higher, right? It's going up and down. It's periodic. It's periodic. Now, can somebody tell me, is this really periodic? Or if I let it go, and this is 3.5 seconds, right? If I let it go for maybe 1 hour or so, what will happen? What will happen? So let me increase some of these uh, values, B and Q. Let's say B equals say 1.8, and this is equal to 1.01. So let us run it again. See, it's catching up. It's catching up, getting more and more energy, right? Getting more and more energy. So you can simulate it in various ways. Okay. And somebody asked whether I can share the codes with you. Of course, I can, but as I said, I want you to give it a try. This is not a very difficult code to write, but anyway, I'll share it with you. I'll put it on the website. You can download and play around with it, right? Uh, and also, I'll check about the signs of this friction and all, right? And let you know. Right. So uh, now, so let's go back to the slides. There's a question. You can unmute your mics and ask the questions, right? It's pretty efficient. Otherwise, when I notice it, your question may be just little too late, okay? So unmute your mics and ask if there's any questions. It's not a interruption to me, and I like it that way, to do it that way, right? Okay. So the answer to the question is that this is not the linearized model, right? This is running with the exact dynamics. So let me show you the code, right? This is the code you are running here. You're seeing here, right? Now, if you look at over here, this part, right? Um, I'm selecting the first line over here, right? This is like a junction that you're coming to a junction and there are three ways to go, right? After that, you combine again, right? So I'm running the dynamic simulation, which is basically an ordinary differential equation solver, ODE45 in MATLAB. I use that one, right? Uh, uh, and in my code, card pinned, right, I send these parameters and I want the OD45 to run for T span. This is the time, simulation time, which is like 3.5 seconds, right? With the initial condition x0, right? So this is to simulate the open loop nonlinear dynamics. Open loop nonlinear dynamics. So if you go to the card pinned, right? I think I have it over here. Here, this is card pinned. This is another MATLAB code, okay? And there you can see this code receives these parameters. So what are they? X, M, capital M, L, G, B, Q, and U. So the parameters and the control signals and the states, right? And you can see it over here, the nonlinear dynamics. So this is the nonlinear dynamics, okay? Dynamics means rate of change of the state variables. So if you have the state variables, and if you have the four equations here about the rate of change of the four state variables, you can routinely run it, right? Recurrently run it. You run it once and update the state variables with the rate of change, and then run it again with the new states and the new rate of change. So you can run it for T span, the total simulation time. Okay. So when you run this discrete simulation, rate of change to the next state and so on, right? You better use built-in MATLAB functions like OD45 rather than you write it your own way, right? To make it more accurate. So there are a lot of a number of solvers. We call it solvers, okay? Differential equation solvers in MATLAB. Just use them. So this is what I do to run the ODE, simulate ODE45 in MATLAB. Just spend a little time and figure that out, how to use ODE45 and what sort of parameters you want to send to simulate it, right? All right. So let's come back to our presentation. All right. So what we learned up to now. So the first bullet here, most plants are inherently nonlinear. This is the reality in the world. There are a lot of nonlinear components, dynamics in most of the plants that we see today. So when you model accurately, you will see these dynamics, right, in your equations. The second bullet says that when you try to model a plant, right, you try to catch as much as possible, right? Which means friction, some sort of damping, all these things, as much as possible, you have to catch, not to miss anything. Okay. So why? Because you want to have your model to be reasonably accurate. Okay. It has to be something that reflects the plant dynamics, right? Uh, to a significant level so that you can use it, not only simulate the plant, but also to develop a controller. Third thing we learn is that uh, the nonlinear dynamic model, right, can be linearized around an operating point. And you saw that we set theta approximately equal to 0, then sine theta becomes theta approximately, cos theta becomes 1 approximately. So these nonlinear terms like sines, cosines, and theta dot, we assume to be approximately equal to 0. So theta dot square becomes 0. Like that, you get rid of the square terms, sines, cosines, and all the nonlinear terms, right? By assuming that you operate around a certain state, okay? And it has to be actually a equilibrium state, okay? Now, if you pick up in this inverted pendulum case, theta equals 45, right? It is very awkward operating point, right? You can mathematically make it, but you will not be able to get rid of the nonlinear terms there, because how can you say sine theta equals theta then, right? So your assumption, line of assumptions break. So therefore, you have to make sure operating point is physically an equilibrium point, right? So that most of the nonlinear terms are actually not nonlinear around that point. It's not any point, okay? Right. And also, when you linearize a plant, right, another advantage is that you will see the variables getting separated out so that you can somewhat clearly see your state variables. What are the state variables? If it was not very clear at the beginning, now when you linearize, when you get rid of some of the nonlinear complex relationships in your math, right, the state variables come clear. It come like coming up to the surface of water, something that was underwater, right? You immediately see uh, what are the state variables and the connections of the state variables so that you can figure out the state space model quite easily. By the way, state space model is inherently linear. So therefore, without linearizing a state space model, it is difficult or impossible to write down your state space model. So anything that you want to do with the state space model, right? If you want actually do that, you have to get your state space model built first. And for that, you need to linearize the plan. Okay, this is how things are connected together. The last bullet, the linear model of the plant, right, can be represented by a set of first order state equations in the form of state space model A, B, C, D. I think everybody knows about it. D is almost always 0. C is the output matrix. B is the drive matrix. A is the system matrix or connection matrix. So this is the summary up to that point. Any questions, please?
So if we add the friction to the model,
Yeah.
will we be able to linearize the model? That means kind of a question that since you are mentioning about the friction and state space model, actually, what I'm talking about. Will
Yeah,
we?
yeah. So it's non-linear. Friction is non-linear. Damping is non-linear. Uh, your non-linear model will have all of these things. But when you linearize it, there's no problem, because when you linearize, all the nonlinear terms go out. Then nonlinear friction part goes out, right? But if there's something related to linear dynamics in terms of friction, that will remain in the model. Okay, so otherwise all the nonlinear terms will go out, eventually leaving only the linear terms. Like static friction, you can add, it's a constant, right? But viscous friction, again, is a linear one, right? Theta dot times the angular, the friction coefficient. That can be added, but theta square terms, yeah, unfortunately, they will go out of the equations. Is that clear?
Yes, it's clear. Yeah, yes.
All right. So, as I said, we are on a journey. We are not taking part by part and scattered. No, it's a like storytelling, evolving story. Now, what we are doing with uh, uh, the pole cart problem, right? One thing is this: if you want to control the plant, right? Now we have to think about a controller. So one thing I would suggest is uh, say something you have already learned in this semester. What is that? Tell me a controller that you have studied in this semester, just a few weeks ago. Do you remember?
Deadbeat control.
Say it again.
Deadbeat control.
Deadbeat. Okay, that's another controller. That's an optimal controller, right? That's an optimal controller. So let's leave that aside for a while. Deadbeat means bang bang, right? Bang bang control. So it's like switching control, right? You completely turn it on and completely turn it off. If you may have seen Apollo 13 movie, if you have not, please watch it. Okay, one of the greatest endeavors of mankind, Apollo 13. That space mission, they couldn't make it to the moon, but they were able to safely come home, right? So therefore, we call it successful failure. Successful failure. It was not successful because they didn't land on the moon, but it was successful because we didn't lose the 2 astronauts, right, or 3 astronauts. So they swung around moon, and then came home. So it's a fantastic movie, not just movie, it's the real story, because they had a problem on the way to the moon. They had a problem, an explosion, right, in the space module. So they lost their cryogenic fuel. They didn't have fuel to make it to the moon and come back, right? It's a deadly situation. And they were not able to turn the spaceship around and come back, right? It was not made for that kind of thing, I think, back then in 70s. So only option they had was still go further up to the moon and go around the moon and get the momentum as you pass through the moon, get that velocity, and then come back with that velocity back to the earth, right? Because they didn't have fuel to get back to the earth. And in one few second footage of that movie, right? They are actually igniting the engine with whatever remaining fuel. It was a deadly thing, right? Whether you want to ignite the engine or not, because already there's an explosion. The moment you try to trigger it, the whole thing will end up in a big explosion. But anyway, they took the risk because there was nothing else to be done. And luckily, there was no explosion and the engine started. They need to fire it up and keep it full throttle for a certain period of time. So it is bang bang control, or deadbeat control, right? You fire the engine, fire the actuator at full throttle and keep it for a certain duration. So full throttle duration, and then you turn it off. That's it. Okay. So the other phase of the deadbeat control is go to the negative maximum and keep it there for another certain period of time. So in that particular mission, only one phase: turn the engine on for a certain duration, right? And after that, let it go, shut it down. and it is a free fall towards the earth. Otherwise, you could have gone anywhere, not to the earth, right? They could have gone around the earth and swing back to the space. All these possibilities were there, but they did this part of deadbeat type of control precisely, and they came home, right? So that's why I'm saying what we are learning here is not fancy stories, right? There's a very serious applications. Now, deadbeat is not what we are going to do here. Why don't you remember the state space, state feedback control? Have you forgotten that? Just a couple of weeks back. Pole placement regulator or state feedback control. That is one thing we can do, right? And the other one is, of course, you have not heard yet, LQR, linear quadratic regulator. Right? You can use state feedback control or linear quadratic regulator and to stabilize the plant. Now let me show this to you, as you can see on screen, right? This is the linearized plant. The linearized plant, okay? You already know A, B, C, and D, right? Using A, B, C, and D, you can design the controller. This is the controller, this part. Sometimes it may not look like what you have already seen as controller, but as I explained some other time to you, I don't have any particular picture in your mind as a controller, right? There's no such thing. It can come in various forms. What we do here is that this is the state space model of the plant, linearized model of the card pole. What it gives out is states, 4 states, right? X dot, theta, theta dot. So you take all these 4 states here, right? And there's a little thing over here, right? I'll explain with that little why. And these 4 signals, right, are combined together and multiplied and added together to generate what? To generate U, this control signal. Okay. So this symbol KU, don't worry about it. We are not actually multiplying K and U. We multiply K and X. If you remember, state feedback control, the feedback signal is actually the feedback gain K times the state. So you have the state feedback multiplied with the gain, and that's the control signal. That is the policy. That was the policy, right? If you refer to state feedback control nodes, you can see the control policy U is equal to minus Kx. You can see it over here, minus Kx. Sorry about this U, it should be X, okay? X is the state variables. Now, when I say X, sometimes you might confuse what X is, right? X has multiple meanings. Now here, the card position is X. Card's velocity is X dot. That is one thing, physical variables. But when I say X in state space, this is not card's position. So this is a vector. This X is vector. It has X, X dot, theta, theta dot. All 4 states. Okay, right. So you measure all these 4 states, and each state is multiplied with a gain here, K1, K2, K3, K4. So it's a row vector of size 4 and a column vector of size 4. So we multiply like that, right? 4 elements and 4 elements, and you get a single scalar, that is U, right? Control signal, it goes to the plant. Now this is what is called the state feedback control. State feedback control. Only one problem remains. How do we calculate K? And for that also, if you refer to the notes, how we calculate the state feedback control, we call it pole placement. You can see how we do that. Pretty easy. The second control is the linear quadratic regulator. That is also full state feedback type of control. right? I'll explain you that in a while when it comes to the slides. Now, when you calculate either the state feedback controller, right there you calculate the gains, 4 gains, okay? Because 4 states, there should be 4 gains. Or the linear quadratic regulator, same way, right? You have K, LQR gain, linear quadratic regulator gain, and the 4 states, right? These gains are different, but they have the same format, 4 elements, 4 elements. Now, for both of these techniques, you need A, B, C, and D. A, B, C, and D. All right. So using A, B, C, and D, you calculate the gains. But once you calculate the gains, when you simulate, you don't need to simulate the linear plant. Okay, not necessarily. You can actually have entire nonlinear plant over here. Okay, because that is the reality, right? For the controller design, you use the linearized model because you can't use the nonlinear model to design the controller. But once you have the controller and want to simulate the plant, I think it's good if you use the nonlinear plant dynamics here for the plant. Okay, remember that. And I also want to tell you this little distortion here, right? The first variable, state variable, is actually position of the card. Okay. Now, both of these controllers, state feedback control or LQR, linear quadratic regulator, they're all both regulator type. Regulator type means they try to bring the state variables to 0. All of the state variables, x dot theta, theta dot to 0. So when you have the pole, right, initially, it is deflected, right? X is somewhere, and there's some theta. Also, you can have some velocities, initial condition. The objective of the controller is to stabilize all these 4 variables, 0, 0, 0, 0. That's it. Now, this is the standard regulator problem. Now, here, there's a little difference between what we want and what the regulator is doing, right? Maybe 3/4 are okay, right? We want angle to be 0, angular speed to be 0, and cart's velocity to be 0. But we don't want cart's position to be 0 all the time, right? We want to move the cart at any position and stabilize there. So therefore, the regulator is the regulator action about the cart's position is not exactly what we want. So that is why we adjust it over here, not to have any confrontation with the controller. We adjust the feedback part this way, right? Your desired position of the cart, let's say 0.5 meter positive or 0.5 meter negative, whatever it is, you put it over here, desired position, and put this block plus and minus. So when the feedback comes, actual position comes in, right? It goes to the positive terminal here, and your desired position goes to the negative terminal here. And the result goes to the controller. Controller doesn't know that you have added or deducted a certain amount from the state variable, right? The purpose of the controller is to make sure that what comes from here is 0 at this laser pointer position. Controller will try to bring that variable to 0. That's what it does. Now you can understand if I want to have my reference at 0.5 meters, when I put it over here 0.5, right, it becomes negative 0.5, right? So when the x is 0, this part is 0, 0 minus 0.5, and your result is minus 0.5. Okay. Controller doesn't like minus 0.5. It will try to make it 0.5. Sorry, 0, not 0.5. So therefore, it will, without knowing what he was doing, the controller will try to make this part 0. So when this signal becomes 0, this signal becomes 0.5. So 0.5 minus 0.50. That's how 0 comes over here. All right. So we deceive the controller this way so that it will drive the cart to 0.5 meter. Okay, simple technique. Any other questions about what you see on screen now? In terms of structure of the controller, feedback, states, controller, and the desired position adjustment, anything? Right. Let's go through some of these things. Full state feedback controller, right? Control law is U equals minus Kx. And this is how it works, right? K1, K2, K3, K4. These are the states, x dot, theta, theta dot. When you multiply, it becomes a scalar. Right? The scalar goes to the plant and change the state, okay? Controller design involves determination of K1, K2, K3, and K4. Now, let's say, I think state feedback control is pretty clear to you. You can refer to the notes if you have forgotten it, but it is something we have already covered. Okay, when you have the linear model, you can calculate the state space, state feedback control. What is new though is the LQR. So let's spend a little time on LQR. LQR is an optimal controller, meaning that you can use LQR to minimize something, right? You want to move the plant from A to B. So when you do that, you want to spend minimum fuel, minimum time, or some cost minimization. Okay, total cost you can minimize. When I say cost, you can define it the way you want. Some people want fastest motion, so it's a minimum time. Some people, they don't want fastest motion, but they want minimum energy, minimum electricity consumption. So reduce the energy consumption, whatever it is. So you have some cost and you want to minimize it. And you are going to control the gains accordingly. That is what is called LQR. So the LQ means linear quadratic. R is for regulator. Linear means this is working for linear plants. Okay. Of course, now our plant, we have linearized, so there's no problem. Second letter is Q for quadratic. Quadratic means, square terms, right? So very famous quadratic cost function is this, right? If you see quadratic control, you will see it everywhere, right? So what is this? X transpose QX. This X is actually the vector, right? Here you have X dot theta dot. This 4-tuple vector, right? Transpose. And there's a matrix in the middle and then X. So it's a row vector and the square matrix and the column vector. Okay. So if I draw these, right? So this will be like row vector like this. And then we have the column square matrix in the middle, and then column matrix like that. Okay, so this is 4, sorry about that, 4 by 1, sorry, 1 by 4, this is 1 by 4, this is 4 by 4, this is 4 by 1, right? So when you multiply, this will be eventually 1 by 1. Okay, so which is just a scalar. Just a scalar. Now, when you have a very big x, right? State variables go up and down, plus minus, right? They're big. So the scalar eventually is going to be big as well, all right? Because any negative states, when you put it into this equation, it will result a positive quantity because x is multiplied with x again, x square terms. So eventually this will have x square, x dot square, theta dot square, right? You know what I mean. It is the square sum of the states and also multiplied with some gains, right? Within the Q, it's like a diagonal matrix, right? If you have along the diagonal 1, 1, 1, 1, this will be simply x square plus x dot square plus theta dot square, sum of square terms, right, of the states. But if you want to have higher cost for x and theta and lower cost for x dot and theta dot, you can change the diagonal elements accordingly, right? So you think any non-zero x or non-zero theta as a high cost, right? And you want to reduce it more than x dot and theta dot, you can adjust the numbers accordingly. And also control signal here, how much of an effort you are taking, right? U transpose and U, again you get square terms. Here U is a scalar anyway, not like X. So therefore this is just U square times R. R is a gain, weight, cost weight, okay? So by adjusting Q and R accordingly, you can get the total cost, right? Your effort and how the state variables change before they stabilize, right? You can have huge variations before stabilization or maybe small variation before stabilization. So the latter one is probably low cost, whereas the former one is high cost. So LQR will look at that. It will check all the different possibilities and eventually find out the lowest cost. And then it figures out what sort of gains you require, right, in order to achieve that lowest cost. So it doesn't depend on poles, right? We are not going into poles. We are going through how the state changes, what sort of control action you are taking, and then try to reduce this cost function. So that is why I call it is an optimal control, okay, some sort of least cost control. So how can you do the LQR calculation in MATLAB, right? It's very simple. It's only this much. You have the A matrix. This is the linearized model of the card-pole system, and you have it, right? The moment you assign values for simple M, capital M, G, L, etc., the matrix, you know it, numerically known. And you know how the control signal comes in using this B matrix, right? In your model, B is already available. C is the output matrix, and for linear quadratic regulator or state feedback controller, you need all 4 states, right, measured, and they're available for feedback. So therefore, C has to be an identity matrix, 4 by 4 matrix with all diagonal elements 1. That is identity, right? Remember, if I pedal back and showed you something we had earlier, this one, right? See, this is output matrix. If you want to pick up x and theta, but if you want to get all of the 4 state variables measured as feedback, then this C matrix will be an identity matrix of 4 by 4. Okay. All the diagonal elements are ones. Off diagonal elements are zeros. So y will be just x. In that case, y is equal to x. Okay, right. So we were up here, right? Measures full state. All 4 states are measured. And D is, of course, 0, right? We don't consider that non-zero. Then you can put a name, any name for the state space model using A, B, C, and D, right? All these 4 parameters, A, B, C, and D. You give it to MATLAB command SS, and then you assign the state space model as cardboard, right? Fine. So this is the state space model. But what we want is to calculate the gains, feedback gains, right, for the linear quadratic regulator. So we have to assign, I will skip this part and come over here, the Q matrix and R matrix, because linear quadratic regulator tries to minimize this cost function, which involves Q and R. You have to tell to MATLAB how big is the cost of the state variables and how big of a cost is the control signal. Sometimes you might say, I don't worry about the control signal. I can use any amount of electricity, any amount of fuel, that's okay. But I want the least amount of fluctuation in the state variables. I want to keep state variables not changing much. And you can use any fuel you want, right? That is one policy. And also you can say, no, I don't have that much electricity or fuel supply, right? I have to reduce that as much as possible. But on the other hand, I can handle some changes in the state variables, right? If they fluctuate up and down by a certain amount, that's okay. So that is a different policy. So whatever it is, you have to tell it what is Q, what is R to the MATLAB to calculate the LQR gains. So this is what I have said in this simulation, 10, 1, 50, and 100. So what does that mean? You have to see it in relative terms, right? This is the cost weight for X. This is the cost weight for X dot. This is the cost weight for theta. This is the cost weight for theta dot. And if you look at these ones, the highest cost is theta dot. So I'm conveying to MATLAB, right? Theta dot, angular velocity, is the most troubling thing to me. Is most troubling thing to me. And after that, theta. Theta is the second most troubling thing to me. Theta means theta away from 0. Okay, is the most troubling thing. Second most troubling. Then x, that is the position, right, is the third most troubling thing to me. Anything off 0, right? And x dot is the least troubling thing to me, right? X dot. So in other words, I can tolerate x dot to a highest level, and then I can tolerate x to a certain level. Then I can tolerate further to a reduced level theta, and theta dot is very difficult to tolerate. Okay, So I want theta to be 0 as much as possible and let the other variables to change a little bit. So I communicate that to MATLAB. And if you look at R is 1. I'm really serious about the cost for R is not that great. Okay. So I don't really too much worry about the control signal. You can have big control signal. That's okay. Right? Because this R1 means is a cost weight. What sort of a cost? Right? How significant the control signal as a cost. 1 means not that significant. So I don't really worry about the control signal being too high or how much of energy I'm using. Okay, so in that you will see this is not very logical or appropriate. I just picked up something reasonably reasonable. Okay, not the perfect setting over here. And then is one single command in MATLAB, LQR. Just one command, LQR within bracket A, B, Q, and R. A matrix, B matrix, Q matrix, and R matrix. And some of these things are not actually matrices, but we generally say matrices, right? And gives you out this variable K. K is the vector of 4 elements. These are the gains, right, that you multiply each and every state variable with, and then add together. So multiply, add, multiply, add, multiply, add, multiply, add. Then you get the scalar, that is U, control signal, and you feed it back to the state dynamic model. So now I want to go back to what we skipped here, rank of controllability matrix, rank of observability matrix. Controllability between A and B, observability between A and C. You have to check this and make sure the system is observable and controllable. Okay, observable and controllable. Any questions, please? Right. Now let me go back to MATLAB. And uncomment, comment this line and uncomment this line, right? So in this line, what I do is I simulate the pole placement regulator. Now, there is a regulator, controller, right, which will try to stabilize the plant. Now, there you see, it doesn't swing all over, right? But it moves to the left initially, and pole actually falls to the right. And to avoid further falling, it moves the pole to the right again. So it's a left-right motion. And it goes to the right. I think the reference point is like 0.5 meters. I want the pole to be stabilized at 0.5 meters, right, to the right of 0. So there you can see x position and x speed, right? In blue color is the x. So you start off with almost 0. Initially, it goes the negative direction, not the positive direction, right? But it's only briefly, and after that picks up motion to the right direction. And now it is reaching 0.5. It's almost there now, right? Stabilized. It's a one single motion, right? Now let's say we want it to move to the right, but it doesn't move to the right initially. Right? Instead, it moves to the left. Because when it moves to the left, the pole swings to the right, and then you move it to 0.5. You can't straight away go to the right, then pole will swing to the opposite direction. So you have to come back anyway. You are in trouble, okay? So if you want to go to the right, you have to go to the left first. Okay. So this is what is called the non-minimum phase dynamics of the plants, or non-holonomic behavior, right, of the plants. It's like a car. When you want to take a left turn, you have to initially go to the right and then take the left turn, okay? Something like that. The system dynamics tell you how these things are affiliated or related to each other. Is that clear to you? So I will share the code with you. You can now run either online, offline simulator, just the open loop control, and then you can check the state feedback. And also I can tell you if you can let us get a sniff of this right, for the later use. Just put it over here. Right, this is state feedback control. Then let us come back to the same code, and this time I'm gonna comment out the state feedback controller and uncomment the LQR, right, linear quadratic regulator. Okay, so let us run it again. This is the behavior when you have the linear quadratic regulator. Again, you can see it swings to the left first, negative x direction, to get the pendulum to fall to the right, the proper direction, and then it starts motion to the right. Okay, and it does it in an optimal way. It doesn't go back and forth, back and forth, back and forth, and try to settle. It's not like that. It's a very well planned motion. Okay. I think it's almost there. Now you can see pendulum is reaching 0.5 meter position, right? And the velocity is also stabilizing to 0, right? So both happening at the same time, right? It's almost there, done. Now we get another sniff of this one. To our slide. This is what we have. The top one is, you can see it clearly now. Look at that. This is same scale, almost, right, from the simulation result. The top one is state space or state feedback controller. The bottom one is LQR controller. So what do you see? What is your observation here?
LQR stabilized much quickly.
Yeah. So you follow these graphs, right? this is actually theta and theta dot, angular position and velocity. The LQR, right? It does not allow theta or theta dot to change much, okay? The deflection is very small or smaller compared to the deflection that you experience in state space or state feedback control. So we already see the control performance, right? LQR is better than state feedback controller, because as you know, state feedback controller, you have to assign the poles, right? And you don't know whether these poles are the best positions, but you give it some reasonable performance, right? To get to some reasonable performance, you set the poles and then you get that. But if you look at LQR, right, it is an optimization process, right? And then you calculate the gains in an optimal manner. If you set your cost function properly, right, which is this one, this Q matrix, right, and R matrix, depending on your how expensive the variability of the state variables and how expensive is the fuel or energy that you have to spend in the process. You can minimize that function and MATLAB will find the feedback gains for you. All right. So I think it's time for a break. We'll take about a 10-minute break. All right. Let me show you this result from another simulator. There you can see these 4 states on the same timeline, okay? Position of the card, X, and then in red, in blue, in red, velocity of the card, and amber, angle of the pendulum, and in purple, the angular speed, and green color is the control signal. Okay. We'll go back to MATLAB, but after analyzing this result. So what we see here is that this is the position of the card. Eventually, we want to get the card to 0.5 meters. Okay, positive 0.5 meters. However, right, initially you can see it over here or maybe over here. The control signal goes to the opposite direction, negative direction, right? And pull the card the negative direction, not the desired direction. If the reference position is negative, this could have been in the opposite direction, right? Positive direction. Then it is controlled in a particular manner. That it comes back and to the right direction, and then pushes the card forward, okay, in the positive 0.5 meters. And if you enlarge this, in fact, here you can see 2 similar instances, right? At time 0 and some other time. There you can see initial condition and the reference. So there's another time instance, not only 0. There's some t reference that is 5. Right, at 5 seconds, now you can see it over here, time axis, 2 seconds, 4 and 5 seconds over here, right? X reference is 2. X reference is 2. In this particular simulation, initial reference is of course 0. You have 0, 0, 0.2 and 0 as the initial conditions. If there's no reference, the regulator, either state feedback or LQR, will try to bring all these state variables, 4 of them, to 0. Okay. And at 2 seconds timestamp, we set the reference, X reference, to 2. All right. So this reference change happens at time 2 seconds. So therefore you see this a spike over here, right? Similar to the big spike at time 0. This spike is because the initial condition, the angle is like 0.2 radians, right? Initially, 0.2 radians initially. In order to recover from that and establish the 0 position, right? Angle, uh, it provides this huge negative torque, okay? And then it stabilizes to 0. So now the initial error has been recovered, eliminated. Now it is stabilized. And then at 2 seconds, we change the reference to 2 meters. So then again, it goes again, right? Like that. So there you can see time 0, enlarged view. You can see the initial offset. All these 3 curves are starting at 0 because the 0 here, 0 here, and 0 here. But the third variable, that is angle, is 0.2 radians. So therefore, it starts with some offset, 0.2, okay? This is what needs to be stabilized. Send it to 0. And that is why this control signal is big and negative initially. All right. Now here, the positive angle means anti-clockwise, Usually the default positive angle direction for angles is anti-clockwise, right? So it moves to your left, positive angle is 0.2. So to prevent it from falling, the cart has to move to the negative direction. So for that, you need to have negative command. That is why this command is negative, okay? Right. So why I'm going through all these things is to set an example for you that when you do simulate something, you get a result, you have to critically evaluate the result. You have to verify that what you see on screen is actually correct, okay, and it represents the reality, okay. So that's very important, right? Now let me proceed a little bit. Now, what we learn in the second part of the lecture, right? 3 things. One, LQR needs all states be available for computing the control signal or force on the card. So that, remember that, right? You need all 4 states here. Now, if you want to shape the performance, control performance, right? More towards the state variables, so that the state variables won't change much, or more towards the control signal, so that the control signal will be not very aggressive, limited, right? You have to tune your matrices like Q and R. Now, what if we have a big Q matrix than R matrix? So elements in the Q matrix, right? The norm of the matrix, right? Q is greater than R, right? Which means numbers are big in Q than in R. So what we're telling to MATLAB is that, what we are specifying basically is that it's more costly to have big state variables than having big control signals, okay? So therefore, we are encouraging to have bigger control signals and smaller state variables. So bigger control signals, you put huge amount of control action and you maintain state variables minimum, right? So that is very aggressive response. We call it aggressive. Or if you said R matrix big, right, like 100, 150, and then Q matrix, the elements are small, 10, 20, like that. So then we say that it's very costly to have big uh, control signals, because R big means cost is high, right, for controls. So we want to reduce R as much as possible. But there's no big issue with having big signal variations, right? Before you are stabilizing, signal goes up and down. So that's okay. The second case, right? So that is basically a sluggish response, right? Very sluggish. It takes time and all, but you maintain the control signal very small, right? Not making it big. So there are two ends to the story: aggressive response or sluggish response. Whatever you want to do, right? Once you set the matrices Q and R, it will do that. So even though LQR is a certain optimal controller, right? So what it does is it tries to minimize the cost function that you specify, right? So it is up to you to specify the cost function depending on your situation, right? Whether you want to have aggressive response or sluggish response, right? Based on the energy or cost in whatever form. But if you go to quadratic, you have to go to quadratic if you want to have LQR. It has to be the quadratic regulator, right? So like x square terms, u square terms. And if you have so many state variables, you have to get square term of each and every one and add together, and then give a relative importance to each and every state variable, right? Yeah, so you are in pretty much in the center of the controls. You can specify whatever you want in the cost function. So LQR is a type of a optimal control. We will do optimal controls probably next week or after in 2 weeks, right? Some theories behind optimal controls, and it has Pontryagin maximum principle and also Hamiltonian Jacobi equations. Very interesting area, a bit more theoretical, a lot of matrices involved, but it's really fun to have optimal controls. All right, next up is state estimation with Kalman filter. So now the problem here on is that you need all the states for feedback, right? That is a problem. You want to measure car's position, car's velocity, pole position, pole velocity, right? So having sensors for each and every one, it's not certainly the way forward in controls, right? We want to have the minimum number of sensors to measure maybe one or two state variables and then estimate the other state variables. Remember, we did the observers, okay? Before the state feedback control, we did the controllability, observability, and we looked at the observer design also, right? The purpose was to replace some of the sensor requirement in the plants and reduce it to minimum, essential minimum, so that other sensor feedback can be estimated. So the most famous, renowned state estimator is Kalman filter. Kalman filter, right? So it does two things. One is it helps you eliminate the noise in the sensors, right? Noise in the sensors, and also estimate the accurate position, right? Velocity or state variables. So that's why the Kalman filter comes into the picture now, or state estimator, okay? Kalman or otherwise. So every time you have a sensor to measure a certain quantity, right, that quantity is contaminated with the noise within the sensor, right? Even though the manufacturers try their level best to reduce the sensor noise, right, there still is a certain amount of noise in the sensor, right? And they know it, and they usually put it in their data sheets. The sensor noise is this much. Now you can do this noise elimination using signal processing, right? Kalman filter is a digital filter basically, right? It's not a hardware filter. It doesn't have any caps and transistors or resistors, right? It's a digital filter. It's process the signals, right, in digital format, and then estimate uh, the true sensor signal, okay, using noisy sensor feedback. So you get noisy sensor feedback as input, and you give out clean sensor signal, okay. So that's why Kalman filter is extremely important. But for Kalman filter to work, there are certain other requirements. Like for example, Kalman filter needs the sensor noise be Gaussian. You know Gaussian, right? Sensor noise distribution should be symmetric and Gaussian bell shape, right? And zero mean. So there shouldn't be any bias, right? Mean error is zero, and it goes negative, positive by equal amounts, okay? When you get a negative error, get a positive error next moment, like that. It swings back and forth around zero, right? If you add all the noise parts of the sensor signal over a long period of time, they add up to zero. That's why I call it zero mean. And also it needs a noise covariance, meaning the variance, right? How wide the noise distribution bell shape curve is, whether it's a very steep one, narrow variance, or like a broad one with a bigger variance. So you can have zero mean, but very wide variance, big variance, or zero mean with a very narrow variance, right? So I think you know what variance is. It's like when you sit for an exam with, let's say, 4 subjects, right? One guy scores 50, 50, 50, 50, all 4. His mean is 50, his variance is 0, because there's no variance. All samples are at the mean value 50. But another guy has the same mean 50, but the marks are 40, 60, 30, 70. It's a wide variation. Not a single grade he has scored exactly 50, the mean. They're all over the place, but average or mean is 50, but there's a big variance. So the theoretical presentation of Kalman filter, we are not doing it today, but depending on the time availability, we'll do it at the end of the course, okay? The equations and all Kalman derived. So Kalman filter needs a linear model of the plan, like ABCD, state space model. With that, you can connect a Kalman filter to the cardboard problem. Because if you look at what we know already, we know the dynamics of the cardboard, A, B, C, D, and D, we know that. And also, what are the sensors that we use here? We know that. Sensor noise, we know. And states, we know, right? And control signals, we know. So therefore, by combining these things, you need to generate something more, right? So that's what Kalman is doing, Kalman filter is doing in estimating the sensor signals, right? We are not actually using direct measurements from the sensor for feedback, but we send it to the Kalman filter and ask Kalman filter to estimate a better value, not the raw value you are getting out of the sensor. Okay, remember that. You have a sensor, maybe a position encoder for card's position, right? Position encode. You don't read it and send it to the controller and generate the control signal. No. Now what you do is you send it to the Kalman filter and provide other signals also to the Kalman filter and ask the filter to tell the position. The Kalman filter will give you the position which is slightly different to actual sensor signal. And the estimate of the Kalman filter would be more accurate than the direct sensor signal. Okay, for some people, this might be not very convincing, and a lot of people think if you get the reading from the sensor, that is more accurate. No, it's not the case, because unless you have a very, very high precision sensor, where noise and variance are nearly zero, okay, then even if you put a Kalman filter will also tell you the same thing. Okay, there's nothing I can do more than what you already have. The sensor signal is already good. Go ahead. It will estimate something which is very, very, very close to the sensor signal. Because when you tell to the Kalman filter, this is the covariance, noise covariance. Covariance is very, very small value. So therefore, Kalman filter understand this is a very high quality sensor. Okay. Is everything clear up to now?
Yes, sir.
Okay. So I think I need to show you this before I continue with the presentation. For that, I will pick up this one. Right, now you can see I use Simulink to assemble the system, right? Right. So what you can see over here is that this is the plant over here, right? Earlier, I had the linear model of the plant. If you remember, it was this one. I don't want to open the Simulink block again for this one. This is ABCD, linearized state space model of the card system. But now, what we have is this one. What is this? This is nonlinear dynamics. This is the, in MATLAB, you can open, right, MATLAB function. If you just click on the, if you click on the screen, right, you can double click actually, right? Just click on screen, double click MATLAB function. So when you just write MATLAB, the first thing comes up over here is MATLAB function, right? Like that. Then you can open it and write your code like that. Okay. Right. So this MATLAB function, I have written the nonlinear dynamics. If I double click, you can see what's inside, right? So what's this? This is the nonlinear dynamics. Right? So this is theta double dot angular acceleration. This is equation number 9 or 10. I don't remember exactly. So if I go back here to the equations, we can find that out. The nonlinear equation, this one, equation number 11, theta double dot, and equation number 10, x double dot. Okay. So these two equations are directly written over here. You can see it over here inside a MATLAB function. Okay. So this function will give out x double dot, that is linear acceleration of the cart, and theta double dot, angular acceleration of the pole. Okay. Once you give it to it, what? xd, u, theta, and theta dot, right? So these are the things that you go send into the MATLAB function in order to execute these two equations. All right. Now, these are the inputs. These are the inputs. These are the outputs. So when you create this MATLAB function, right, it gives you this function command here, and you can put anything in here as input to the function and anything here as output to the from the function. So outputs are coming over here, right, and here, right. Theta dd and x dd. So I think I have written the same thing again over here, multiplied and expanded. So I think one is enough. One is enough. This one is enough. Okay, right. So the moment you set these ones, MATLAB knows what are the inputs. So how many inputs are there and how many outputs are there, right? So it will generate this input-output format here, two outputs and 4 inputs. All right. So it will label what I have written here, x, d, u, theta, theta dot, like that. So it gives out acceleration in of the cart and the acceleration of the pole. So then I have one integrator to get to the velocity of the cart and another integrator to get to the position of the cart. All right. And this one integrator to get to angular velocity and another integrator to get to angular position. An angular position is a input to the function itself, and cart's velocity xd is also input, and pole angle, pole velocity is another input to the function. So theta dot, and xd, right? So these are inputs to the block. In addition to that, control signal u comes as an input. So control signal comes from the controller. Now this time we have linear quadratic regulator, LQR. So that will generate the control signal. So I think this part is clear. Okay. Now what happens is that this line is cart's position. This one is cart's position. And we have a sensor to measure the cart's position, right? Position encoder. Some sort of position measuring equipment, right? Sensor. And this block tells you the noise in that measurement. And this is going to be the sensor noise. And so is the problem. And at the same time, we have theta here, that's the pole angle, and you can measure it. In this case, we are not actually using it for any obvious reason, but you can measure it using another sensor, and this is the noise of that sensor. Okay. These blocks you can double click and open and set whatever noise power here, right? So the four states, this one, this one, this one, and this one are connected together using this demarks, and then send it to the MATLAB workspace under the name of state. Okay, so that in MATLAB I can access this data. So the control signal coming out of the controller is also sent to the MATLAB workspace, right? Combining with the states. I have the control signal also as an array. I write it to the workspace under the variable state. So that once the simulation is over in Simulink, I can go to the MATLAB code, right? And proceed to draw the graphs and all. Okay, right. Now what I try to do is that I want to take the cart's position here, right, and combine it with the control signal, this one, and send it to Kalman filter. This is the state filter, state estimator, right? It runs the state space model of the plant. If you see, right, it is ABCD. If I double click and open it, you will see this is the system Kalman filter A, B, C, and D. Okay, and initial conditions is 0, 0, 0, 0 because filter doesn't know any initial conditions, right? But the whole card's position, angle, speed, it doesn't know anything. So we by default set initial values for the Kalman filter to be 0, and we expect Kalman filter to pick it up and quickly track the actual states. Okay, right. So now we are not actually measuring 3 state variables. We measure only one, which is this one. Okay, and I send it to the Kalman filter as a block, MATLAB block. Okay, I generate the Kalman filter in my code. If you go to the code, you can see it. Yeah, this is the code for that. And if you move down, this is A, B, C, D. We check the rank of controllability metrics and observability metrics. That's all fine. Then the LQR regulator, right? You can see now I have changed a little bit over here. Take freedom to change it, right? The way we want, right? Now I think this one is given high cost, which is the third one, third state variable, the angle, right? Now I say angle is the most precious thing to me. I don't want the angle to change much, right? So I give 100, okay, as the cost for that. And also together with that position, because I know I want to bring the car to a certain point and then stabilize. Angle and the position. This looks more sensible. Right. Then what else? I use the LQR, right? ABCD, that's LQR controller gains, right? Because now, if you look at the LQR, that is the controller. A Kalman filter is to generate the state variables, all right? So please make no mistakes here, right? LQR is a controller, right? It takes state information as feedback, either directly from the sensors or through the Kalman filter. So you anyway go ahead and design your LQR without any difference, right? And after that, we build the Kalman filter. So for that, we give W, which is the sensor noise covariance. You will see it's a very small signal noise I have set here, right? Because Kalman filter cannot handle big noise, should be small noise, right? And V is the covariance for the second sensor, but we are not going to use it here in this simulation because only one sensor signal is used, right? Then the Kalman filter command, here we generate the Kalman filter using LQR command. This is another LQR system, in other words, okay? In other words, if you look at the internal structure of the Kalman filter, it looks very much similar to LQR, right? So therefore, you use the LQR command to generate your Kalman filter also. So don't be surprised because of that, okay? But the arguments, what you give it to are different. A transpose, C transpose, W, and V. Those are things you pass on to this LQR command to generate your Kalman filter. And you have system KF, you generate the Kalman filter over here actually as a system block, all right? So once you do that, you have system KF, right? System KF as a block, and it has a lot of elements, A, B, C, and D. So when you access elements, you set system KF dot A, syskf dot B, and so on. So these are the values. You can see it over here. Not this one, this one. If I open Kalman filter block, I can see syskf dot A, syskf dot B, syskf dot C, like that. Okay, right. Now all these parameters are actually generated here in the MATLAB code. All right. What else? So then the Kalman filter generates, right, all four states, 1, 2, 3, 4, all four states, right? And we use it to feed back to the controller. Now, controller takes the Kalman filter estimates, right? If you can see very clearly here, the four states are actually not going directly to the controller, but there are only one signal, right? Only one state is actually going to the Kalman filter. It generates all four states. Now see how beautiful this is, right? And then we have no problems with the feedback controller, LQR, right? So let's give it a try and see. So if this works, we get rid of 3 sensors altogether. We only need one sensor. Right, so let me go back to the MATLAB code here. It is this code which runs the Simulink block, all right? This one. So this is the result, right? Only one sensor, that is the position of the car. So now think about it. If I give you this problem, right, cart pole problem, and I give you only one sensor to measure the position of the car, and I ask you to use the sensor information and also the control signal, A, B, C, D, and anything, but can you generate all 4 states, right? This is what we are trying to do here. Now you can see the result. What's going to happen here? So X and estimated X, you can see it over here. Blue color is the actual X. Red color is the estimated X. So it's pretty close to each other. Now you can see it over here. Can you see that? This is the noisy sensor signal in blue color. Noisy sensor signal in blue color. Red one is not a physical signal. It is generated by the Kalman filter now. See how closely it generates the signal. It gets rid of the noise, but make it very clear. Okay. This is what Kalman filter is capable of doing, right? Now, this is theta and theta estimate. Actual theta, even though we don't have a sensor, we know the value because we are simulating it, right? If you get that information and compare it with the Kalman filter estimate, you can see that Kalman filter tries to estimate even the angle of the pendulum, right? Which looks very, very difficult to do, right? Because how can you estimate the angle of the pendulum with only knowing the position of the cart and the system dynamics and control signals, right? A lot of information is available, but how could this be possible, right? So it is very difficult to convince that any possibility of estimating the angle of the pendulum, right, without directly measuring it. Okay, but here you can see for some time, Kalman filter has been able to track the angle, right, of the pendulum up to about 6 seconds, right? It is doing a pretty good job, but it is not possible to do it indefinitely after 6 seconds, right? Kalman filter estimate, which is the red one, right, is way off from the blue one, which is the actual position of the angle of the car, right? So this is a very good experience for you to understand the reality of the Kalman filter state estimation. And some people think that it can do anything. No, it has its own limits. This is the standard Kalman filter. We sometimes don't call it standard Kalman filter. We just say Kalman filter. It's a linear state space model based filter or estimator. So therefore, it has its own limits. Now you know it pretty well. Now, if you look at on the left-hand side, you can see x dot, theta dot, and u. Now you can see the control signal is very ugly, isn't it? Not like earlier. Right now, things are not very normal. So things are far from being perfect. We have only one sensor signal. It's difficult to maintain any optimal or clear control performance here. Right. The purpose of showing you this result is for you to understand what the reality is in control systems. Okay. It's not a fancy world. It's very much realistic, and you need to know what is out there for you to make use of, and then what are their limits. Okay. Right. Remember this graph. The Kalman filter can perform up to a certain level, right? It's not bad or it's not perfect, right? So you need to know the limits. Now, going forward, right? Now, let me bring you inside the Kalman filter, okay? The system with the sensor noise looks like this. Now, this is x dot, right? State space model, x dot equals, this is matrix A, AX plus BU. But now we have plus this term. What is this? This is the sensor noise. This noise, right, affects the rate of change of the control signals. This is what the noise is doing, right? So there you can see this sigma square of the first signal, second, third, and fourth, right, with W1, W2, W3, W4, right? This is the random noise between -1 and +1, right? These are random numbers, right? And this is the relative covariance, right? When you have the sensor on the data sheet, it gives you about this error covariance. And this is for the four states, right? And this is the measurement part, right? You have this state vector and the output matrix, and you pick up, say, the first one, only the first one, others are 0. You measure the distance, okay, the position of the card, and plus 0 u, there's no control input, plus again you have standard deviation of the sensor noise and the random v. This is the randomness, is the noise, okay, Gaussian noise. So this part is actually, even though we call it noise, this is actually the process noise, process imperfections, right? This is very much part of the system. Now, say in reality, x dot equals ax plus bu thing, right, is not complete. You always need to have this little thing here as process noise that we do not know, right? Any system is like that. If you just follow x dot equals ax plus bu, right, you will see it's different from the actual states, because there's always something that is unmodeled, right? That is what's called the process noise. You need to capture this one. Right? Kalman filter allows you to capture this one. If you know about the process noise, this is nothing to do with the sensor. This is very much internal to the process. Inside the process, if there's anything, right, that is not modeled, but you know this type of variations are there, right? Kalman filter allows you to specify all 4 state variables as similar to a noise, okay? And this is actually the sensor part. Why? We have one sensor here. That is why this is 1, 0, 0, 0. And this is the noise of that sensor noise. So you need the covariance of the process, that is W, this one, right? And covariance of the sensor, this is this one, V. And I have set very small values to make it a point. And rest, I think I have explained to you. So this is how you design a Kalman filter, right, in MATLAB. If you go through the code, this is how you do that. Okay. Now there are 2 ways you can design a Kalman filter in MATLAB. One is in your MATLAB code, you can code like this, right? Everything. And then open MATLAB, right? Simulink, sorry. And there you have Kalman filter as a block, right? And put the values in there. So yeah, like that. So double click, say Kalman. When you write down first few things, you get the Kalman filter, right? Like that. So this is Kalman filter. And then go inside and fill these things, right, about your Kalman filter. Then you're good to go. So it's so easy in MATLAB. All right. Now, what we do now is that we understand that measuring only the card's position is not adequate, okay? You need to measure the pole angle also. So let's add a rotary encoder to the pole and try to measure the angle, right? Now you have the position and angle both. So I think we can expect a better performance, right? Now, while we are doing that, I want to tell you this also. Now, the linear quadratic regulator when you connect it with the Kalman filter, right, we give it a different name. We call it LQG, linear quadratic Gaussian controller. Right? When we have only the LQR, linear quadratic regulator, and you have the direct measurements, it is the standard LQR. But when you have a Kalman filter, to estimate the states using a fewer number of sensors, and the estimated states are fed back to the quadratic regulator, we call it linear quadratic Gaussian, right? So now what we are doing is actually linear quadratic Gaussian. Right. So right. So what we learn up to that point is that, so there you can see a few slides over here. I might be able to skip that one, right? It's of the same sort, like there you can see X and estimated X, pretty good, right? X estimation has no problems. If you got this kind of result, you can enlarge this portion and see very clearly how close the estimate is, right? But if you look at the pole angle, right, it goes like that, theta and theta estimate. Sometimes it goes pretty good, right? You can see it over here. And for very small angles, right, you can see it over here. Initial error is 0, 0, 0.1, and 0.0, right? So this is very small initial error in theta, right? It's able to capture it, and plant is stable, therefore no problem. Now, if you have a good estimation, the LQR will stabilize, so therefore it will not show huge deviation in the state variables, so that it is again easier for the Kalman filter to estimate in the second loop and third and fourth and fifth and like that, right? So this is a win-win situation if you start with a very small initial error. But if you have a big initial error, like 0.2 or something initially, then you might be in trouble, right? Somewhere here you can see the angle is very different, so performance is not good at all, right? Maybe this is because of small noise, increased noise or something like that. So either you increase the noise or change the initial conditions, they both affect the accuracy of estimation. So when the Kalman filter is not able to estimate accurately, right, the controller is going to be deceived. Controller will take inappropriate action, so it will not be able to regulate the plant properly. So it will reflect badly in the consecutive control loops, cycles, and things will go out of control easily, right? As you can see it over here, some of these curves, they are monotonically increasing, right? The system is unstable. Okay. Right. So what we learned here is that state estimation is an efficient way of producing state variables for full state feedback control, such as pole placement or LQR, right? So you have the controller, just a matter of estimating the state variables. However, the plant needs to be observable. If the plant is not observable, you can't do this, okay? So you have to check the observability first. Then Kalman filter removes noise in state variables. You saw that the red line and the blue one, it is able to eliminate noise and get the signal part portion very shrewd manner. But again, I have to tell you that if the noise is too big, even Kalman filter cannot handle that situation, okay? Because the filter is a linear filter anyway. So estimation of loosely coupled state variables. This is a situation here. The angle of the pole and the position of the card are very loosely coupled. The coupling is not very strong. So therefore, estimating the pole angle using the measurement of the card's position is not that easy and accurate. Okay, so this is one of the problems we encountered here. So in that situation, you need to, your options are actually to increase the number of measurements, right? So therefore we say um, use a rotary encoder for pole angle measurement, right? So let's measure the pole angle. Right. So we are actually coming to the end of the session today. Probably we can pull it over. So when you add another sensor, the measurement vector becomes a matrix like that. Okay. So you are taking x and theta now, two measurements. And therefore, the sensor covariance matrix becomes 2 by 2. And you have to read the rotary encoder data sheet and figure out the noise covariance. And also you have to figure out the linear encoder noise figure and put it over here, right? So in MATLAB, this is how you do that. Covariance matrix, it's like this for the process noise, and covariance matrix for the sensors are like that. It's 2 by 2 matrix. Okay, right. Then you use the LQR command to generate the Kalman filter and all its elements. Like once you have syskf, you can get A, B, C, D from syskf, right? Then your system will look like this, right? With the Kalman filter with two signals, right? One is the position of the card, the other one is the angle of the pole. They both go into the Kalman filter here, right? You can see that. In addition to that, you have to send the control signal also to the Kalman filter, and it will produce the 4 state variables, right? Still the same Kalman filter, okay? Same means standard Kalman filter based on the linear dynamics. So let us go to MATLAB and take that. I think it's this one. The code is being compiled. Okay, so now we have something. Right, you can see it. This is the x and estimate x, right? You can see it's going like that, right? It's not able to stabilize in this simulation, and theta and theta estimate is gradually going out of tracking, you know. Kalman filter is trying to catch it, but in this particular simulation, it's not possible, right? So maybe we need to do something about it. Let's reduce the covariance a little bit and see, or the initial values of the, yeah, it's a big value here. X0, see 0.75. That's why. So let us take like not 75, 0.2 or something, right? Same errors that we did earlier. And let's put this back to what it was, right? Probably this time it will work better. Yeah. Can you see that? So this is under the same circumstances that we have been having all this long. Initial error is like 0.2 degree, 0.2 radians rather. Okay, it's not very small. Now the Kalman filter, this is the linear Kalman filter with two sensor inputs with their noise and all. Now it's able to do a better job, right? This is X, which is going to say like that. And probably looks like it's going to saturate here or level off at 0.2. So let's see what is the reference point is. That is X reference is 1 actually. X reference is 1 and the P X reference is 10. So therefore, I have to check this not to 10, maybe 5 to see what happens, right? So at 5 seconds, it changes the reference, right? Position to 1 meter, but let me take it like 0.2 meter, right? Otherwise, it will be out of my scope. So see what will happen. Right. So at 5 second, right, I set the reference to 0.2, but it goes like beyond that, right? Is it 0.2 or 0.5? I said it's 0.2, right? So maybe it's too small of a reference, or let's say yeah, 0.4 something. And because of this fluctuation and right. So now you can see that 0.4 is the reference and it goes beyond that, but it will come back if you give it enough time, right? So why don't you give it some more time and see? The total time is how much? 10. Let's call it say 20. 20 seconds, okay? Now you can see what's happening. So the reference is 0.4 meters, somewhere here. Now you see the control is trying to get to that point, but it's not able to do exactly that. Maybe if you wait and see for a long time, it might do the job, but it looks like it will just swing around that point. So if you can develop the animation for that, you will see the cart is going like that and just trying to swing around. But what about the pole? Pole is also swinging back and forth, right? Because of this motion. Both these things stabilize simultaneously. You can't have one to stabilize the other one swing, right? It doesn't happen. So now you're getting somewhat closer to the reality. See the noisy signals and this oscillation. This is the reality. Most of the MATLAB figures that you have seen are not actually real. They are like hypothetical or ideal signals, very nice curves, first order, second order rise and all that, right? In reality, these are the kind of type of signals that you see. All right. So we have included the sensors, the noise, and also say just two sensors, but to predict 4 state variables using Kalman estimator. That's a quite an undertaking, right? So I think you studied a lot on that. Right. So what's next? we have quite a lot to do. 32 slides, we are at 24. Let's move on a little bit further. Now, what's next? What do you think? How can we further improve the situation? Well, now to improve the situation, we need to know what the problem is, right? I think the one major remaining problem in the control system is that the estimator here, right? This estimator uses linear model of the plant, okay, whereas the actual plant is highly nonlinear, okay. So the estimation process, right, inside the Kalman filter uses the system dynamics. It uses the system dynamics and estimate or predict the state variables. Now, if the actual system is little off from the operating point, the linearized state, this estimator is not able to accurately predict the state variables. Okay. To get rid of this problem, what we can do is that, what we can propose is that we'll try to improve the Kalman filter so that it is able to use the nonlinear dynamics here of the actual plant. You get that point? So if you can bring this dynamics, right, from the plant to the Kalman filter, right? We might be able to improve the situation if we can do that. Okay. We just need to try to bring the dynamics of the plant from here to here. So actually this has been done already, and if you do that, the Kalman filter gets another name, new name called extended Kalman filter. Okay, extended Kalman filter. So if you go back to the historical notes in, I think it's 60s, when Rudolf Kalman presented this filter at a forum, right, in US, he presented the standard Kalman filter, this one, okay, standard Kalman filter, based on the linear dynamics. Then there was one person, I forgot his name, he's from NASA, US Space Agency. He was in the audience, right? In fact, he was thinking about a problem. He was dealing with the terrible problem of the spaceship guidance and tracking and all that, okay? Because this is a noise-based problem. He always has to deal with noise, how to estimate the position of the spacecraft, orientation of the spacecraft, and so on. So when he saw this Kalman filter and state estimation emits the sensor noise, he picked up the point, right? And he also picked up the problem, right? The solution and the problem together in one go. He picked up the solution, that is the Kalman filter, state estimation, and also he picked up the problem, the linear model. Then what he did was he went back to NASA and maybe took a couple of weeks, tried to improve the dynamics. He wrote new equations, and he gave birth to the extended Kalman filter, right? Now here also, what we are going to do next is we try to replace the Kalman filter with the extended Kalman filter. All right. So there's some slides, additional slides. Okay, this is using the standard Kalman filter, but now big angle 48 initially, right? But it's still able to stabilize the plant, right? But you can see some errors here. Theta and theta estimate, they don't go together, right? All the time. There are errors at times. So I'm showing you the limits of the Kalman filter, right? The performance is not that good with single sensor, but the two sensors, we have some better performance. But again, when you have bigger errors, initial conditions, right, big offsets, again, that won't help. So we need to improve the performance of the filter. So we generate a new Simulink model for that, right, with the extended Kalman filter, together with the standard Kalman filter. Now, you understand all of this, right? All of it is already clear. Only new thing over here is this block. This block. This is the standard Kalman filter. Standard Kalman filter. This is the extended Kalman filter, right? So now let me explain you what the extended Kalman filter is. So let me go back to MATLAB and open yeah, this one. All right. Actually, I was running this one earlier. Anyway, so now if you look inside the extended Kalman filter, now let's see first the wrapping around the extended Kalman filter, right? So you can see there are three inputs to the extended Kalman filter. The first one over here is the control signal, right? You need to send the control signal that you are giving to the plant, right? Also to the Kalman filter, because it's also an estimator. Estimator is running a copy of the dynamics, okay? So you have to send the control signal that you send to the plant. Now, the second one is this signal, right? What is this? This is the measurement, right? This is the measurement. Now, yeah, so the measurement goes to the as another input, and the other second measurement is this one, right? So in fact, I need to make a little adjustment here. We need to take this one from here actually after the sensor noise, okay, because that is the sensor signal, and this one is actually from here. So let me make that connection from here to here, or maybe from here. Yeah, and this one should be taken after the noise. So it should be like this. Okay. So the extended Kalman filter takes the measured position and measured angle, right, as y1 and y2, and it produces x hat. And the earlier simulation you saw is from the standard Kalman filter, this one, right? So in this code, I can delete this and connect this signal to that signal, so that I will get the state extended Kalman filter to generate the states, and that goes into the linear quadratic regulator. Okay, so let's give it a try. There you are. All right. Now this is a much better clear signal now. You can see the position and estimate goes like that, but it's not kind of stable, right? It's not very stable. It goes like that. But tracking wise, it's okay. It tracks the angle and position pretty well, right? If we run for some more time, we don't know what's going to happen, right? But it shows a very good tracking and estimation performance. Right, okay. So now if you look at inside of the extended Kalman filter, right, I can probably show this in MATLAB code itself, Simulink model. So if you open up this one, you will see this dialog, and you need state transition function. You need to have another MATLAB code for state transition. This is basically the discrete time state transition that you did in earlier weeks, right? The nonlinear model, basically, the rates of change of the state variables. You have to write it in a code, right? MATLAB code. And also you have to tell what the measurements are. Here, the y1 and y2, right? Measurements. And also covariance of the measurement, covariant 1,1, covariant 2,2, right? You have to provide that from the covariance, noise covariance matrix, which is 2 by 2. You have to say this is the first element on the left up corner, and this is the right bottom corner, 2, 2. Okay, right. And also, when you use the extended Kalman filter, which is always discrete filter, you can't connect analog signals to the filter. Before that, you have to convert it to digital, discretize, and that is why these discretization blocks are there, okay, which were not there in the standard Kalman filter, which can accept an analog signal, okay. All right. Now, if I open these blocks, like state transition function, measurement function 1, measurement function 2, because two sensor readings are there, measured readings are there. They are also MATLAB codes. So let us open it, open state transition function up here, right? So that is it. This is the state transition function inside the extended Kalman filter, right? So it has X and U, right? X is the state, U is the control signal, and these are other parameters that you need in the equations. So X equals X plus this thing times delta T. So this is basically state updates from the previous state X plus rate of change times delta T, okay? And the rate of change of the second variable and the fourth variable are like that. Okay. And also measurement, if you look at the measurement function 1 and 2, both are very similar to each other. This is the measurement function, just one line, y equals x1, right? The output is basically x1, right? So you measure x1 and then you measure the other one. What is that? This one, x3. So you tell that you are measuring x1 and you are measuring x3. That is the position of the cart and the angle of the pole. So once you furnish those information to the extended Kalman filter inside, you code it, right? And you have y1 and y2 from here, right? It knows how to update the state. Okay, so that estimation would be more accurate. All right, so that's all what I want to discuss today with you. So this the remaining few slides will explain you the internals of the extended Kalman filter, measurement functions, state transition, and so on. So this one over here, you see the true angle and the angle with the noise, right? And the Kalman filter estimate and all that. So you can see some sort of some errors are still happening for large initial errors. So therefore, it also has its own limits. Okay, none of these things is perfect, right? They have their own limits, right? Here's some of the control performances. When you have 0.75 radians per radians initial condition, huge initial offset, right? You definitely can't do anything with the linear controller, but this is a non-linear extended Kalman filter. Now see how we handle the situation pretty well. Whereas with the Kalman filter, standard one, you will never be able to recover it, right? It goes further down and down and down. That's it. Any questions, please? Is everything clear?